Hello students, welcome back to Math 332 Elementary Linear Algebra. So if you remember from the previous video, I keep saying that we can actually take a basis which might not be orthogonal and convert it to a basis which is orthogonal. Orthogonal basis simply means that, just as usual, basis which consists of vectors that span the space and independent, but we impose another extra conditions. That is, all the vectors in it has to be orthogonal to each other. They have to be orthogonal to each other. So this vector is orthogonal to this vector and orthogonal to this vector, so on and so forth. So the best way to think about it is that our E1, E2, and E3, our x-axis, y-axis, and z-axis, those are the standard way, the standard orthogonal basis that you know. So the question is, if I have a vector space, I have a basis for that vector space, but the vectors in it might not be orthogonal. The dot products of those vectors might not be 0. And so I would want, because of some application purposes, I would rather work with bases that have vectors that are orthogonal to each other. And how do you actually do that? So this process, Gram-Schmidt process that we're going to talk about in this video, will give you an algorithm, a procedure on exactly how to convert a basis that might not be orthogonal and convert it to an orthogonal basis. And let's get right to it. All right, so let's first look at the objective for this video. So at the end of this video, you should know how to construct an orthogonal basis by applying the Gram-Schmidt process. So if I give you a set of bases, which, the vectors in it span the space and being linearly independent, you should be able to perform this Gram-Schmidt algorithm and build a new set of bases, which obviously still span the space and being linearly independent, but now they have the property that every vectors are perpendicular to each other, which means the dot products of vectors, they are different. Those dot products will be 0. And based on your it's almost end of the semester now. So based on your understanding of linear algebra and all the concept of span and the concept of projections and all that, you should know why this process, why these procedures or Gram-Schmidt algorithms work, okay? Now, so let me be clear on what we actually wanted to do, okay? Let me spell it out for you. So we are in this Euclidean space Rn, and we have a subspace W. So assuming that that subspace W has this basis, so these are the vectors that span the space and being linearly independent, but they are not necessarily orthogonal, okay? It doesn't have to be 90 degrees, so to speak, okay, to each other. So we want to construct a new set of bases by doing something on this original set of bases. So we want to convert this into another basis, which obviously still span the space and being linearly independent, but this time all the vectors are orthogonal, okay, 90 degrees to each other. Okay, so how do we do that? Right, so in order to do that, before I spell out the algorithm for you, let's look at a simple case, okay? Let's look at a very simple case involving two vectors, and we'll build from that, okay? All right, let's recall a concept that we've been talking about for many times, but let's do that again very quickly. So you have a vector u, and you have a vector v, and we want to project this vector v onto u, right? So this is called the projections of vector v onto u, right? So it will be the vectors that is pointing in the directions of u, okay? And having this particular magnitude right here. The length of this vector is this much, okay? And the directions of this vector is in the direction of u. So now, if you move these vectors, change the directions, okay? Move this vector right here, okay? Move them, change the directions of the projections, and I'm looking at negative of the projections of v onto u, so that's the negative, right? Which means that we have exactly the same length of this vector, but now the direction has been reversed, and then translate it and put it here. So now you see that v plus just the negative of this projection vectors is going to give you this, right? So this vector right here in black, this vector right here in black, that is v minus the projections, okay, of v onto u. All right, so we know that. So we know that this vector, we have been talking about this in the previous video. We know that this vector is perpendicular to this vectors. Okay, this vector here is perpendicular to this vector. You can kind of see the way I draw it, right? You can kind of see that this is the case, but we can't really prove things using picture. Okay, so we the way we verify it is we take the dot products and show that the dot products between these vectors and this vectors is 0. Okay, so this is what we have seen before, and we have also figured it out how to actually compute this projection vector, and that's the formula. Okay, so that's the formula. All right, so the question now is, how do we use this, okay, to orthogonalize a basis which has only 2 vectors? So let's look at this particular example right here. Now, in this example, we have a vector space W, which is spanned by these 2 vectors, x1 and x2. All right, so obviously this one here, these 2 vectors form a basis because they span the space. Obviously, that's how we define them. And just by visually inspecting these 2 vectors, you see that they are linearly dependent. So we have a basis. So we have a basis. This x1 and x2, this form a basis. These are the vector in the basis for this vector space W. Are they orthogonal? Are they perpendicular to each other? Oh, how do we do that? How do we check that? Let's take the dot product. x1 dot x2, and you will see that if you multiply this together, you have 1 times -2 plus 1 times 0, that's 0, and then times this is also 0, and you get -1, which means that even though these are the basis vectors, but they are not perpendicular to each other. They are not perpendicular to each other. This is not a 90 degrees. It is not, okay? So how do we construct another basis? But this time they actually is perpendicular and still span the same space. Okay, you cannot just say that, wait. This is in the R3. That's easy, right? Why don't we, just make the E1, E2, and E3s to be our basis? Well, because this one is 2-dimensional, right? So the basis is going to be something like that, So you to construct an orthogonal basis is not as simple as, oh, okay, let's just pick 2 of the orthogonal bases like the one that we have seen easily. Like, so pick the let's say the z-axis, pick the x-axis. This is orthogonal. It is orthogonal. This is really orthogonal. The black one here is really orthogonal, but they don't span the space, right? So it is not as trivial as you think. It would be like, wait, okay, so this is no good. So why don't we just use this one instead? Well, this is orthogonal basis for some other vector space. It might not be this vector space. Okay, so the way we can actually construct a new orthogonal basis for this particular vector space is pretty easy. It's not so difficult. And the idea is actually spelled out in this diagram right here. This diagram basically spells out everything you need to know on how to proceed. Okay, so let's do that. All right, let me draw you a picture and show you how this is done. Okay, so now I am taking my x1. Okay, this is my x1. This is the vector right here. And let's call it V1. Okay, let's give it another name, V1. All right, so now I have this x2 somewhere. We know that they're not orthogonal vectors. x1 and x2 are not orthogonal vectors. So let me compute this projection vectors, same as before. Let me compute this projection vector. Let's call this the projection of x2, right, onto x1. But since we just renamed x1 as v1, so let's just do that. Repeat the same process, okay? Reverse the direction of that vectors. That's minus the projections of x2, right, onto v1. And then if you now look at the sum of this vector and this vector, this will give us this vectors. So this vector right here is, what is this vectors? This vector right here is x2 minus the projections, okay, of x2, right, onto v1. And we already know from our previous knowledge, our prior knowledge, that this vector right here and this vector right here is orthogonal to each other. This is orthogonal. This is orthogonal. They are 90 degrees. Okay, so perfect. So we call this x1 as v1. So now this is our v1, right? Our v1 is our x1, okay? All right. We are now going to call this vector v2, right? So we are going to call this vector v2. So your v2 is this vector right here. So you can see that we have two vectors now. These two vectors, v1 and v2, they are independent. All right, they are independent because this vector right here and this vector right here they are independent. Okay, now the only thing that we need to do before we can claim that this is actually an orthogonal basis, right, for W, is that we have to show, what do we need to show? We know they are orthogonal. Once they are orthogonal, once these two vectors are orthogonal from our prior knowledge, we also know that they will be independent. So they are independent, definitely independent. Orthogonal vectors, non-zero orthogonal vector is definitely independent. So the only thing is that, all right, seems very cool. We constructed two orthogonal vectors and coming from x1 and x2. But how do you actually know this is the basis? What is missing? The thing that is missing here, which is not very clear, is that the span, okay, the span of this v1, v2 right here, right? Is it exactly still the same as the span of the u1, u2? This is not clear at the moment. At the moment, this is not clear. Do you agree? Right? The only thing that is clear is that they are orthogonal by the way we construct them. Okay, by the way we construct them, these are orthogonal. Okay, they are orthogonal. V1, V2, they are orthogonal. But how do we know they actually still span the same space? Because it's very dangerous. Because you are in R3, you have a plane, right? This is W. We have a basis that's right here on the plane. And who says that when you are constructing this orthogonal basis, you take this one, right? How do you know that the other one that you constructed will not be getting out of the plane, right? So the span part is something that we need to check, okay? And this is pretty easy to do. We just have to make some observations, but this is pretty easy to do. And we are going to look at it now, okay? All right, so now we want to come to explain why this is true, okay? So if you look at the notes right here, this is exactly what we just did, okay, in terms of the computations. We want to write it out so that it is clearer. So we did take that v1, set it to be x1. And this entire projection vector here, we are saying that this is v2. So if you do the computations, okay, you can see that now these are orthogonal. This is not a problem. We already know they are orthogonal. Look at the dot product between these two vectors. They are 0. The dot product is 0. They are really orthogonal. That's not a problem. The issue here is that how do we know they span the space? And this is answered by looking at the formula here, right? So V1 is definitely inside the span, right? Why is it? Because the span of x1 is all the possible linear combinations of x1. And x1 is definitely in it, and x1 is v1. So this is kind of trivial, okay? Now, if you look at this formula right here, the way we compute, right? This is exactly the same as x2 minus the projection. We just spell out the entire computation right here. And you can see that v2 is something, right? Is 1 of x2 plus some constant, or if you like, minus some constant, that's number, okay, x1. So by definition, your v2 is definitely spanned by x1 and x2. That's clear. Your v2 is definitely spanned by s1 and s2. Do you know that? Do you know that having this, okay, having this, you should be able to see that the span, okay, of v1 and v2, right? This is a set that is sitting inside this set. This is subset of the span of x1 and x2, right? It's easy to see because everything v1 is in here, can be written as a linear combination of x1 and x2. Your v2 also can be written as a linear combination of x1 and x2. So all the linear combination of this will definitely can still be written as a linear combination of x1 and x2. So that is clear, right? So we have this part of the inclusions. Now, remember, every time we want to show that two sets is the same, two sets are the same, we have to show the both sides of the inclusion, right? A is subset to B, okay? B is subset to A. If you can show this, then A is equals to B. So we are doing that, right? We are doing that. And so we want to have another side of inclusion. So the other side of the inclusions is this. X1, okay, is obviously still inside the span of V1. But you look at x2. So what is x2 in this case? So x2, if you look at these formulas and just move this entire terms to this side. So if you do that, you will get this. Right, so x2, move this across, you will get v2 plus some constants of x1. But don't forget, your x1 is actually v1. That's how we define x1. So again, your x2 is a linear combination of v1 and v2. So your x2 is a combination of v1 and v2. So once we have this, we will be able to see that the span of vector x1 and x2, right, is subset of the span of the vectors that is in v1 and v2. Why is that so? Because x1 can be written as a linear combination of v1, okay? x2 can be written as a combination of v1 and v2. So all the possible combination of v1 and v2, okay, can be all the linear combination of x1 and x2 can be written as a combination of v1 and v2. So because of this, now we can actually claim that the span of the vector that we just constructed, the orthogonality is not a problem. We know that. You can look at the computation. The orthogonality is not a problem, right? This vector here that you constructed, right? The orthogonality is not a problem. We have a very clear picture of what exactly is going on, right? We can verify them by taking the dot product. Yeah, so orthogonality, that is not a problem. The span is not so straightforward. And now we see that the vector that we constructed, the v1 and v2, they still span the same space. So let me draw you a picture. So if you have W that looks like this, okay, your original vector x1 and x2, right, is a basis that's like this, then your v1 and v2 will not do anything crazy. It's still going to be something that is like this, okay, and orthogonal. So your v1 and v2 are still on the plane, okay, so to speak. Okay, nothing really changed. And that's basically spell out everything that you need to know on this Gram-Schmidt process. But this is on two vectors. These two vectors give us intuitions on how this is done. But let us expand this to vector space Rn. And let's say you have a subspace which dimension k. How do we proceed and continue our orthogonalization process? How do we write down a procedure and algorithm? And this is what we're going to do next, okay? Now, if you remember from the previous video, we also actually know how to do projections, not only on a vector, but on a vector space. So suppose you have a vector space, W, okay? It has to be spanned by orthogonal basis. So let's say you have orthogonal basis, V1, V2, all the way to VK, all right? So suppose you have a vector space W, right? These are the orthogonal bases, okay? So V1, V2, this all has dot products equal to 0 if the dot product is performed between two distinct vectors. Okay, now, so let's say you have a vector X right here. How do we do the projection of X onto W? So the way we do it is to, you know, kind of like shine a light right on top of the vector. It casts a shadow. And this one right here, that's called the projections, right, of this vector X onto the vector space W. So be careful on how you write this. So this is different now, right? So this is projections, right, onto not a vector, but a vector space W, and this is your vector X. And we also did a computation in the previous video. Again, we reverse these vectors. This vectors right here is on vector space W. Let's reverse the direction of the vector. So you have it right here. All right. Okay. So this is, again, the negative of the projection vector. Same as before. Okay. Notation-wise, a little bit more complicated. But now you look at this vector X, okay, plus this negative vectors, this vector X plus this negative vectors. Then you will get this vector right here. So let me write this thing down. So this is your X, right, minus your projection vector. Your X minus your projection vector of X onto W. And we, from the previous video, we have seen that this, okay, this vector is actually in W perp. So this is your vector space W, right? And this vector right here is in W perp. What does it mean? It means that this vector is orthogonal to every vector that is coming from W. Any vectors that is from W, this vectors right here will be orthogonal to it. That is the meaning of being in the orthogonal complement of this vector space W. It's a fancy way of saying it, orthogonal complement. But what it means is that this vector is orthogonal to every single vector that is from W. All right, so this is a review. We know that from the previous video. Why do we want to do that? Well, the reason why I want to talk about this is because it will help us simplify our presentations and also our conceptual understanding of what is going to happen next. So now I'm going to give you a procedure called the Gram-Schmidt process. You can, if you're computer science, you might want to turn of it as an algorithm, right? Step-by-step algorithms to convert, okay, a vector space which have a basis U1 all the way to UR to an orthogonal basis V1 all the way to VR. So let me show you the step first, okay? So let me show you the steps. Okay, so step 1. So remember, what is the one that is given? So you are given the U, right? So you're given the U vectors. You're given all the U1 all the ways to UR. And we want to convert, change it to the V. All right, okay, so we want to change it to the V. We want to make all this vector orthogonal, but you have to be very, very careful. You cannot change the span, all right? It's not as simply as, why don't you just take the E1, E2 and all that? No. We have to make sure that the process that we are outlining here will not change the span. We are still in the same space, so to speak. Okay, so the procedures is this. Step 1, you call V1 as your U1. Basically say, let's start somewhere. So let's start with this terms, this vectors that you are giving me, and let's call it V1. All right. So you form a vector space V, which is called W1, which is a span of V1, and you do this projections. All right. So this vector space here is just a multiple of one vector. So this projection is actually the projection onto V1, which is our U1. So this is no big deal, right? So this is basically your step 1 and step 2 right here. It's exactly the same. It's exactly the same things on the example that we have seen before, okay? All right, for convenience, I draw the picture here to illustrate what happened in the first 2 steps, right? First steps here, pick the U1 that's given. You call it V1. So you look at the span. It's called this vector space W, but it's just V1 doesn't really matter that much. Do the projection just like the example that we have seen, and you know that this and this will make this vector, and this vector here, this vector right here is going to be perpendicular to these vectors, and we call that V2. All right, so now V1 and V2 are already perpendicular. V1 and V2 is already perpendicular, so let's build on it. Okay, so let's build on it. All right, so now how do we build on it? Okay, so now as I said, your V1 and V2 are already perpendicular, right? So now you can already have your V1s like this, right? Your V2 like this, they're already perpendicular, right? And you look at this vector space that they span. You look at the vector space that they span, okay? Let's call that W2. Let's call this W2. So W2 is the vector space span by V1 and V2. These are already orthogonal. We need that because in order to write down the projection vectors using that formula that we have to make sure that this vector space here, whatever that is spanning this vector space, they have to be orthogonal, okay? So we have V1 and V2 already. So let's select U3. So U3, okay? Let's take a U3, right? U3 is coming from the original basis. This is the original basis, U3. Where is it? Right here. So we already have changes to U1, U2. Let's take the U3. So U3 will be somewhere right here. Let's say U3. Okay. Now we want to project that vectors onto this W2. Why do we want to do that? We want to project these vectors onto W2. So I am going to project this vector onto this vector space W2. Why do I want to do that? Because if we take the negative of this vector, move it here, and you take this one plus this vectors, we're going to construct another vectors right here, which is U3 minus the projections of U3, right, onto W2. We know that this vector is in W2 perp. It is in W2 perp, which means that this vector is going to be orthogonal to every single vector that is coming from W2. And V1 and V2 are on W2. So in particular, this new vector that you constructed, which you conveniently call V3, is going to be orthogonal to V1 and V2 for sure. You see that? So you project onto this vector space that is spanned by the previous two orthogonal vectors. You project to a vector space that is previously spanned by the orthogonal vectors, and you do this computations. This will guarantee that the new vector you generate will be orthogonal to every single vectors that you have it from before. All your predecessors, you will be orthogonal to all your predecessors, and you just repeat, right? You see that's a repeat. Once you have the V1, V2, and V3, this is again orthogonal vectors. Let's form another vector space. Let's form another vector space. Let's call it W3 now, and do the same thing. Take the U4, right? Project 6 into W2. Do this, okay? Get the new vectors right here, which is U4 minus a projection of U4 minus a projection of U4 onto the vector space W3. This is in W3 perp. This is in W3 perp, which means that is orthogonal to every single vector that is from W3. And W3 have V1 and V2 and V3. And that's how we make sure that the vector we constructed will still be orthogonal to all its predecessors. So you repeat this process until you run out of vectors from the original used vectors. Right, so in this example right here, we have U1 all the way to UR. So we repeat this process to construct V1 all the way to VR, and we stop. All right, we just keep projecting to the vector space that from the previous steps, and take the vectors minus the projections, which will make the new vectors in the orthogonal complements of this vector space, and blah, blah, blah. And you can see that's how we do that. Now, that is no question whatsoever here. There's no question whatsoever here that the vector we constructed are orthogonal, right? So V1, V2, the way we construct this, there's no question whatsoever that they are orthogonal bases. They're orthogonal vectors. But are they orthogonal bases? I mean, they're independent. Orthogonal vectors, non-zero orthogonal vectors is definitely independent. So the only question right here is, well, the span of this the same as the span of this? And the answer is yes. Basically exactly the same argument from before, because we have a way to write down all the formulas. So from the formulas that we have, you can actually be able to repeat this process right here. Sorry that I keep saying, yeah, basically you can repeat this process right here to show that all the V1 is spanned by the U1, V2 is spanned by the U1, U2, and then the U1 is spanned by V1, your U2 is spanned by V1, V2, and you can show that actually exactly the same way, okay, exactly the same way, you can show that actually the span of all this vector here, right, and the span of all this vector here, right, this two span actually give you the same space, so that you don't get out of the space, you never run out of the space, you're always spanning the same space. So that's how we get the orthogonal vectors and orthogonal bases, okay? So once you have the orthogonal basis, it's very easy to change it to orthonormal basis. Well, you just take every single vectors that you obtain and then divide it by its own magnitude to change it to the unit vectors, okay? So now this is an example that we have right here, and I want you to give it a try. So give it a try, apply the procedures that you have just seen, and convert this vectors, okay, which is not orthogonal to each other, right? You see the dot product of these two vectors are not zero, right? The dot product of these two vectors are not zero, so they are not orthogonal. So can you change it to orthogonal vectors using the Gram-Schmidt procedure? And not just any orthogonal vector, you also want to normalize it. That means you want to make it a unit vector so that now you can actually have orthonormal bases. Okay, let's give this a try. All right, why don't you pause the video, take your time and work on that, and I will come back and show you what I have. All right, let's apply Gram-Schmidt process and convert U1, U2, U3 to Q1, Q2, Q3. All right, so let's take your V1 as U1, okay? That's step one. Let's take your V2 as this, just compute that. So now we have this vector and this vectors forget about the normalizations, right? Divided by the unit vector. We don't have to do it until the very end. We just basically repeat the process. Just go through the Gram-Schmidt process. The Gram-Schmidt process say that V3 is U3 minus the projections of U3 onto the space that is spanned by V1 and V2. So we do that computations, right? Okay, this is U3, okay, minus away the projections of your U3 onto a vector space. This is a vector space that is spanned by the previous two vectors, which is V1 and V2, which has to be orthogonal before you can use this projection formula. I mean, the concept is not difficult to understand, right? So this one here will be in W perp. That means it's orthogonal to everything that is in W. In particular, they will be orthogonal to V1 and V2. So no big deal. If you go through this, you can see that this is definitely orthogonal. You can check visually that the dot products of any two vector that is not the same will give you 0. The dot product will be 0. You can double check the dot product of this will be 0, right? So the dot products of this will be 0. Right, so they are orthogonal, and they actually still span the same space. That's slightly difficult to see, but that's not a problem. We already explained that. And if you want to change it into orthonormal basis, well, you look at these vectors divided by its magnitude. This is what you get. You take these vectors divided by its magnitude. You take this vector divided by its magnitude. So this is no longer just an orthogonal vectors. These are orthonormal vectors in the sense that if you take the dot product between these two, you get 0. But if you take the dot product between these vectors by itself, you will get 1. All right, you take this dot product between these two will be 0. Dot product between these two will be 0. But the dot product between the vector itself, dot product of this vector and this vector itself, will be 1. So they are unit vectors. Okay, they are not only orthogonal, they are unit vectors. Okay, they are unit vectors. So that's it. You can verify that again, right? So this one dot this one will be 0. This one dot this one will be 0. Okay, this one dot which one I haven't tried? Yeah, this one dot this one will be 0. So they are orthogonal. Orthogonal implies independence, and they actually also span the space. We checked that already. Okay, so that's it. All right, so this is the end of this video, and I will see you in the next one. See you soon.